Hello everyone, this is Mr. Ege and we're continuing the 3DSTUDIOMAX rocket project from where we left. This is the second part 2 and rockets are actually the elements, vehicles of space transportation, and that unit will enable us to cover these transportation assignments. So we left in the middle of union tail wings, and for to do that I'm going to use top view, and I'm going to select the top view of the rocket is fuselage, and now I'm going to go to the compound objects. Okay, create compound object. As you know, create has multiple options. Okay, is under the list you have standard primitives, extended primitives, compound objects, particle systems, you name it, body objects, and so on. All kinds of doors, NURB side windows, architectural engineering applications, point cloud objects, dynamic objects. I use some of them, and many of them are not. I like to test it myself. Compound objects enables you to join several objects into one. So go to compound objects, and there is a poor probably option. Already the body is selected of the fuselage of the rocket is already selected. So if you go to Pro Boolean, it enables you to select more than one part. Boolean by itself enables you to select one part at a time. So it's in 2 attempts. So I'm going to go with the Pro Boolean. It is not much different, but when you click on it, please pay attention. Before click on start picking, they put it on the top. Make sure that it is union is selected. If you don't select the union, it's going to intersect or subtract. So make sure that union is selected, and then move your cursor over and start picking button. And when it highlights, you can move your object and select the tail wings and click inside and hit escape key. Okay, so everything, all the entire rocket body became one, and that's the very important part of the uh, of this session right now. So, what do we do next? Mass Effects toolbar, we have to have that in, and we're out of the Mass Effects toolbar right now. And this is our rocket. The in 2 phases. The top phase, okay, will be orbiting. The bottom phase, the engine one, and halfway up on the road, maybe it's going to fall down once the engine uses up all the fuel here. So entire rocket, but this is only the geometry of the rocket. So, and we're going to apply mass first of all, so that it gain weight. When it gains weight, then it's going to find its own balance up in the air and on the floor, on the ground. So to do that, um, we need Mass Effects toolbar. For that, you go to animation, and you will remember from the last session, you go to um, Mass Effects, okay, and rigid bodies. Go down to utilities and show Mass Effects tools. Okay, and notice that I'm selecting that the entire uh, rocket, the body of the rocket, everything with the tails and everything has been selected. When you click on it, you're supposed to see in blue aura, and that means everything selected. So make sure that all the numbers that we set earlier on the Mass Effect are the same, nothing changed, because this is session 2. That's why I am making sure that numbers are not changed. Okay, that's a good news. Nothing has been changed. Now, what are we supposed to do? First of all, we're adding a mass to this entity, and the entity itself is supposed to have a gain weight, a particular weight, and then we're expecting this entity fall on the floor, on the ground. So for that to happen, Perhaps we need to move it up a little bit higher. And when I'm doing this one, I'm gonna press the shift button to just send it up in the air a little bit. I'm sorry, do not press the shift button. Just simply drag a little bit up higher. And when the effect of this activity is supposed to fall down after it gains weight and bounce, okay, over the over the ground. That dark line at the bottom, okay, is considered to be ground line, and computer actually, 3D Studio Max, that knows this line, okay, as a ground, so that the object be in touch with the ground, it will slow down and contact and then bounce back. Okay, it's at a certain rate. All right. Okay, so we can continue from here. And one of the things you want to do is go move your cursor over animation and find the Mass Effects. Okay, at the toolbar, pull down menu, Mass Effects, and go to rigid bodies. This will be a rigid body, but there are the three different rigid bodies. Okay, and for example, there's a set this selected as a rigid body. Now the rocket is already selected. And if I set this rocket static rigid body, it will not move at all. So if I have a background or some ground object that's not supposed to move, I would be using this one. So this is not the correct choice for me. Set selected as kinematic rigid body. Kinematic rigid body is for the rockets that you want to move by hand and change the angle and direction and then move again and stop and record it and move again and stop and record it. This is the kind of similar to cinematography technology, square by square or every 10 square, you give a different kind of motion just to control it. I don't want that either. I want this to be as natural as it is possible, as scientific as possible. So I'm going to select the dynamic rigid body. So this rigid body, rocket rigid body, is supposed to be dynamic rigid body. So I'm clicking on that dynamic rigid body. What it does is it will enable me to give the initial speed, go up certain height, maybe 35,000 meters in the sky, and stop there, gradually slow down to the point of stopping at that range, and then start falling down. And after that, everything will be again supposed to end up naturally. Okay, so that's why I'm selecting the entire rocket, the first selection, as dynamic rigid body. Okay, we're not doing kinematic or static, it's dynamic. So click on it. Okay, so you will see some tessellation lines all around it, and it's okay. Don't pay attention. Try to not to see them. Okay, and there's a way to remove them, but right now it doesn't bother me. So I'm going to keep them there wherever purpose they're internally serving. Okay. Okay. So at this point, I want to. So far, we simply assigned mass, material mass, okay, to the rocket. And what we have accomplished, I want to show you the effect of what we accomplished. And because it's already selected, rocket is already selected, I'm moving my cursor on the right hand side, command menu, on the command menu on the upper, I'm clicking on the modify tab, on the modify tab, not the create. It used to be create tab was on, and the current tab is modify. Click, and it shows you pretty much initial velocity. There's a number of other features here, okay, and initial spin and so on. But ultimately, you look at the mesh here and the density. There's already assigned density here. You can see the mass, total mass calculated already on the right-hand side. Mass is apparently 539,565.3 kilogram, even with the density of zero point 0.5. Notice that 1 is more realistic density, right? So all of this, okay, all of this without any force assigned to it, okay, should enable our rocket to fall down on the ground. And how is that going to happen? I'm going to just move my cursor over the MassFX tools, okay, and I'm clicking on the second simulation tool. Now, normally it comes with world parameters tool, which we experienced at that. I'm moving my cursor to next simulation tool, click on it, and now I have the playback simulation screen in front of me. And please don't click anything here except play button and watch for what's happening. It's supposed to fall down, and I'm expecting it falls down. It even bounces back if you see it. Okay, everything falls back on the ground line, and it bounces a little bit back. Okay, and then it stops. That's what I was expecting. Now I'm going back again to replay and click on it, and it's going to take a while to listen to me. It took me second click to put it back where it is belonged to. Okay, so that's exactly what would happen if you raise any rocket to a certain height and then drop it at the speed acceleration at 9.81 meter per second second squared. And computer 3D Studio Max, exactly what it does, it computes based on the acceleration rate and find out its velocity at any given second, even millisecond, and then it calculates, okay, the impact force with the weight and everything, it bounces back and so on. So all of these done internally, mathematically, numerically. What you see on the screen is interpretation of mathematics behind the screens. So that's why I appreciate the 3D Studio Max a lot. It's a very nice and very beautiful simulation program. And I heard from my college professor that the NASA was using initially in after 1980s and so the 3D Studio Max simulations to simulate their own space research and rocket research. So what else can we do? Here's the interesting thing. First of all, there's a math behind this entire thing. If we want this, if we know the mass of this rocket, and if we want it to go certain height, it's at the Earth orbit around the Earth. Okay, we have some math to do. I'm going to take a note of the mass by itself because that makes only sense, and it's going to also enable us to calculate the energies and required. So mass of this particular rocket, yours is maybe different, don't worry about it. 539,565.3, 565, and I'm going to go round it to 66.0 kilogram. This is important. Why? Because fuel is energy is important. Because of energy, fuel is important. How much fuel you're going to put for the launch off, and also we want to soft land it back too. And so we need to know how much energy is going to take a certain height. What is the height distance that you have in mind, Mr. Ege? And ask me this question. I was thinking of at least 35 kilometers or 35,000 meters, and if possible, why? Well, I mean, this is the distance that we can have orbiting satellites, for example. That's very critical. Whereas International Space Station. International Space Station is at 250 miles. That's quite up farther away. But there are tens of thousands of 30,000 plus satellites around the Earth right now. So, and every year is another 1,000 is being added. So this is a huge industry around the world, not only in the USA but around the world. Huge industry, and so there are thousands of more satellites around the Earth every year, and we already have plus 30,000 plus satellites. So I think this is a good area to invest your future and research studies. So what do we do? How do we add? Okay, and what are the calculations obviously needed to find out how far it's going to go, what kind of velocity is needed? Um, so let's take a look at the command menu, okay, where I demonstrate modify page. In the modify page, there are a number of areas, and one of the last item is forces, okay? And I'm not going to do anything regarding to forces, but you can take a look at it, what it looks like, but don't use it. It says use world gravity check mark. That's fine. Don't do anything else. Very good. Go to the advanced feature, the last item. There's a folder here, advanced. So physical shapes, I'm not going to visit the physical shape, so it's going to be there. I'm going to go to advanced features, and I want to show you something interesting. Advanced features will give you access to a number of things. For example, it says solver iterations. I wouldn't touch that. I wouldn't change that because right now, even though this is a little bit slow, the simulation is working fine. Initial motion, absolute, relative is selected, and that's also fine. Okay. Initial velocity is very critical place. It gives you a velocity in three different axes, x, y, and z. X, y, and z, the alphabet's last three axes, 24, 25, 26 letters of alphabet. Okay, that's very important because everything is moving up at a particular axis, and I suggest you to use z-axis. Z-axis acceleration. And I'm going to assign a speed. Okay. Um, how do I assign a speed? That particular speed is very important, and it's going to be initial speed, of course. And 3DSTUDIOMAX is so smart; it can automatically calculate initial speed, and after every millisecond, next speed and next speed and next speed under the influence of uh, gravitational deceleration. In this case, deceleration, because when you're using an initial speed, the rocket moves up, proceeds up in a certain distance, and at the same time it loses speed because of the gravity. Okay, which is that's why we added gravitation as minus 9.81. So initial speed. So I'd like to say 9.81. Why? Because acceleration, and it takes 1 second to lose that. Okay, initial speed. If I add 9.81, and that's plus, by the way, and we're going to lose that within a second. I don't know if you can see it or not, but I'm going to put one there just for testing purposes to show you, demonstrate, and one here. Okay, and rest of it is zero. Please make sure everything else zero. Okay, and then uh, I'm going to play this. Okay, so I'm going to click on this, see if it's going to be, and I didn't even see it. 1 second passed so quickly. 1001, 1002. I'm going to change this to 9.8. I'm sorry, 9.8. That was the initial. And all of it is in the 9.81 in the Z direction. Now I'm going to play this up again. Click. If it doesn't work in the first click, try again. Okay, goes up. Can you see it? Very good. Okay. So what happened is that it took 1 second, literally, okay, to go up, but at the end of the 1 second, it loses the uh, entire initial speed and it starts falling back. 9.8 as being the same number as the deceleration, minus 9.8 of the gravitational coefficient. And when you give and that's exactly what it means. When you add a 9.81 acceleration rate, it takes 1 second to put up against the gravity, and then it starts falling down. If you like to see it again, let me show you one more time. All right, uh, 3, 2, 1, go. Up, goes up, and then falls back. Okay, so everybody see this? And I'm going to just simply save this file. And please, you do that. So don't forget to save. Saving is very important, the original location. All right, so the big question is, I'm going to ask you to take this rocket all the way up to 35 kilometers or 35,000 meters up in the air. And so you need to assign an initial speed, initial initial velocity. I should be using velocity, not speed. Speed and velocity are two different things. Velocities are vector values, speeds are numerical. That's extremely important. On the z direction, I suggest you to discover initially the initial velocity to take your rocket all the way up to the orbit at the elevation of 35,000 meters or 35 kilometers. And once you find out about that, I suggest you to compute the time, how long it takes for that particular initial velocity to come down to zero. And it's going to be a big number, don't worry about it. And right now I can calculate it. I'm adding also the calculation procedure, okay, so that we can have a meaningful flight, okay. And that initial speed is for the flight plan of the rocket. That initial speed is extremely important. That's because nobody can put up with the huge initial speed. I mean, the human body can only put up with maybe 2, 3, 3.5 g acceleration. The acceleration is what your body feels, not the speed. When you assign a speed, suddenly it becomes an acceleration. And that's detrimental to human health or animal health or anything. So initially, first step is to find out about what initial speed will take you to where, what elevation, and then after that, you find out a smoother uh, acceleration rate or rate of acceleration for friendlier to human body, and then reach to the a particular speed that's going to probably halfway, and then gradually reduce to zero deceleration. So all the engines are supposed to be adjusted according to the flight plan, and this is how you do the flight plan. It should be as friendly as human body. So what are we talking about? 9.8 is 1G, considered 1G. And human body, we know, can take 3.5 to 4 for athletic people, astronauts, G or 9.81 times 3.5 perhaps. This is the friendly as the rocket can get initially. So my suggestion is to find out that in the first uh, in human initial speed that can be detrimental to the human body, that it will take the rocket to the 35 kilometers of elevation, and then discover what would be the friendlier approach smoother approach, smoother acceleration to the rate of velocity that will take you that height. Okay, at one point, uh, we're not going to be running engines all the way to the time, starting time and end time. We're going to run the engines only halfway, and then we're going to allow the rocket to go by itself, using up its own potential energy after speeding up a certain point. Okay, so go ahead and please and design your system. Okay, and also please remember one of the interesting things. Uh, how would you know? And you should ask me this question: how far a rocket goes? All right. So there is a measure tape for that. So I suggest you to create a measure tape that is as high as goes all the way to 35,000 meters. And where do you get that? Remember the create button over here? See, there is a triangle. These are called helpers. And over here, there should be a tape. Click here. And the tape enables you to draw a line that is easy to see. If you press, for example, that particular line, I can see the z-axis 170 to 100, okay? And then you can just literally modify total z-axis distance from here, or modify from here. And that should be 90 degrees, specify the length, and length is 100, okay? But that's not long enough. So what is it we want is 35,000, right? So it's going to 35,000 meters. Okay. And now it is 35,000 meters. So I want you to rocket go all the way to follow the line, okay, to the top, reach to the top of the measuring tape, and then start falling down from there. And we're going to record this, and we're going to make a video out of that, okay? And thank you very much for watching so far. And then please start your rockets. And I'm going to be right next to you if you have any problem, if you have any questions. Either way, I'll be with you. Thank you.